So, each of them alleges that the other has made some kind of error in measuring either distance or time or both. And they assign an error which we will call gamma. S prime says that x equals gamma times x prime plus ut prime. Whereas S says that x prime is gamma times x minus ut. They each use the term gamma because each of them is alleging the other is wrong, but neither of them can say that the other is more wrong than they are. How are we going to find out what gamma is? Well, we can take these two equations and multiply the left-hand side and multiply the right-hand side. And so we get that x times x prime equals gamma squared times x prime plus ut prime times x minus ut. And that becomes x prime equals gamma squared into x prime x plus ut prime x minus x prime ut minus u squared t prime t. But now wherever we find t or t prime, we can substitute that t equals x divided by c, or t prime equals x prime divided by c. And that means we get x prime equals gamma squared into x prime x plus u x prime over c times x minus x prime u x over c minus u squared x over c x prime over c. Now we can divide all those terms by x prime, and that gives us that 1 equals gamma squared into 1 plus u over c minus u over c minus u squared over c squared. And that means that gamma equals 1 over the square root of 1 minus u squared over c squared. And that is known as the Lorentz transform. And so we see that if we apply this transform, x is equal to x prime plus ut prime divided by the square root of 1 minus u squared over c squared, and x prime becomes x minus ut divided by the square root of 1 minus u squared over c squared. Notice on this Lorentz term what happens if u is very small compared to c. Then the term in the square root simply reduces to 1, and you get normal Newtonian mechanics. The gamma term is only relevant when u is approaching c, and then it is known as becoming relativistic. We can also work out formulae for time. We know that x prime equals x minus ut times gamma. That means x prime equals x minus u times x over c, because t equals x over c, times gamma. Dividing everything by c, you get x prime divided by c equals x over c minus ux over c squared times gamma. But of course x prime over c is t primed and x over c is t. So t primed equals t minus u over c squared x all times gamma. Similarly, for x equals x prime plus ut prime all times gamma. X equals x prime plus u x prime over c, which is t primed, times gamma. Dividing everything by c, x over c equals x prime over c plus u x prime over c squared, all times gamma. And then, of course, x over c is t, x prime over c is t primed. That gives you t equals t primed plus u over c squared x prime, all times gamma. What is all this telling us? It is telling us that when speeds are relativistic, in other words, getting to the point where the gamma term ceases to be equal to 1, that the distance measured by an observer and the time measured by an observer will depend on the speed of the distance between S and S prime. It may seem odd that time should be different for different people. So let's just explore that a little bit more. Let's imagine that we create a very simple clock. The clock is consisting of 2 mirrors placed 1 meter apart. A light pulse travels between the mirrors and is simply reflected backwards and forwards. Every time it hits the lower mirror, it hits a counter which clicks on by 1 count. We know that the speed of light is 3 times 10 to the 8 meters per second, and we know that the journey from the bottom mirror to the top mirror and back again is a journey of 2 meters. So when that light pulse has completed 1.5 times 10 to the 8th cycles, 1 second has gone past. And so we can make a clock which simply records the number of times the pulse goes up and down. But now let's imagine that that clock is on board the spacecraft S. And we have somebody else observing from a different spacecraft, travelling at a different speed, and he is looking at that clock. Relative to that observer, the spacecraft S is moving along at speed or velocity v. When the light pulse leaves the bottom mirror, the spacecraft will be here. But when the light pulse arrives at the top mirror, the spacecraft will have moved, and so the mirror will have moved. And so the light pulse, instead of going vertically upwards, will have gone at an angle. Similarly, when the light pulse comes back down again, the time it takes from getting from the top mirror to the bottom mirror will mean that the spacecraft will have moved again slightly to the right. And so the pulse will not come down vertically, but at an angle. The observer says that the distance that the light pulse has travelled is further than 1 meter because it has gone up at an angle. And since the speed of light is invariant, it must have taken longer to get up to that mirror than the person on board the spaceship thinks. And that leads to the conclusion which comes from the formula that tells us that t prime equals t minus ux over c squared times gamma. What this is saying is that if I observe a moving clock, I will say that that clock is running slow. Every observer observing a moving clock will see that moving clock moving forward in time at a slower rate than their own clock.